Model answer for question 3, the essay. I'm not quite going to do an essay, but I'll try and break down these points. Systemic versus pulmonary. In the Help Me video we came up with the job that we needed to do. So we're going to use the graph information to explain why the pressure in the systemic looks like that against the pulmonary that looks like that. And those are going to be two major areas. And then we want the single versus the double, or the advantages of the double. So we start off with the systemic circulation. What do we notice first? Well, we notice the pressure is higher. Why is that? That's because the left ventricle has the thicker side, and so more contraction force can create greater pressure, up to 120, whatever these units are, millimeters of mercury in the aorta. So contraction of left ventricle with thick muscle can generate high pressure, 120 millimeters of mercury in the aorta. Why do we need this? Well, we need this to pump blood all around the body. So high pressure needed to pump blood all around the body. It's a long distance, all the way down to your toes or against gravity up to your head. There is a pressure decrease down to 80, and that's due to the relaxing of the heart, but it doesn't go down to 0 because you've got those valves, you've got those semilunar valves in your arteries, at the start of your arteries. So pressure decreases to 80 when heart relaxes. So that is, ventricular diastole or diastole. High pressure is maintained for two reasons really. Firstly, as there is elastic recoil in the arteries, we've got that elastic wall, and the semilunar valves shut, they're forced shut, or the aortic valve, same thing. So that explains this wiggly bit at the start. Why does it go down, start going down? So pressure decreases in the arterioles and capillaries, in the arterioles and capillaries as there's a bigger area, cross-sectional area, and the blood is moving against the wall, which gives it friction. So those are two main reasons, due to blood flowing through a greater cross-sectional area and frictional resistance with the walls. And in the capillaries, then we are losing fluid from the capillaries, losing tissue fluid. So pressure decreases in the capillaries due to loss of tissue fluid. And that's necessary for diffusion of gases and so on. So that's why that's happening. And then in the veins, we've not got zero pressure, we've got some pressure. So small pressure in the veins, and that's due to massaging effect on your veins, moving blood around, due to massaging effect, not by me moving this, but by skeletal muscles. Moving blood. So that's our systemic, and we just need to you don't need to, a lot of that's true for pulmonary circulation as well, but we just really want to highlight the differences and why this is lower. So pulmonary circulation. So why does the pressure increase? Well, it increases due to the same thing, ventricular systole, but of a thinner wall, a thinner muscle wall of that right ventricle. So contraction of right ventricle with thinner muscle wall to generate pressure of, what do we have, 20, maybe 25, 30, that sort of hard to read. Pressure of about 30 millimeters of mercury. So this is a lower pressure due to smaller distance to the lungs. This is one possibility. We'll talk about another reason for lower pressure in a second. So it goes down to about 8. So pressure decreases to 8 for the same reasons as before, due to diastole. And we could mention the semilunar valves, the pulmonary artery and so on. We're more interested in why this pressure is a lot less. So pressure in the capillaries is lower than the systemic, so lower. So pressure in the capillaries is lower than the systemic pressure to prevent damage to the alveoli. And this alveolus, it's on the other side, so we've got blood on one side and it's a very thin couple of cell thicknesses, and then we've got air, so we don't want a lot of tissue fluid being made, so this prevents excessive tissue fluid being formed. It's fine if it was muscle or something, that would be fine, but if it's just an alveolar space, we don't want that filling up with liquid. And then we need just the difference in the two circulations. So, benefits of double circulation versus single. So you could even draw a diagram. You could have single. So we've got a heart. Then kind of really simple diagram there. So pressure is lost. So say if you've got the gill there, then you've got muscle there. So we're picking up oxygen in the gill, then going to the muscle, then back to the heart again. Single circulation. But there's not another heart here pumping blood to the muscles, so we're losing pressure, as in our double. Then essentially blood is going to the lungs, then back to the heart, then to the body. Although it's two sides of the same heart. You could draw a better diagram, but that's the general idea. As long as you make clear it's the left, that'll be the right, and this will be the left part of the heart. So a description of those, and then so pressure in single circulation, pressure is lost. When blood passes through the gill capillaries, and this makes it all slower. So blood flow in fish is slower. Compare that to our double circulation. In double circulation, high pressure can be maintained, as described in the first two bits of this essay. And this meets the higher demands for oxygen by a mammal. All that for 9 marks. 6 of it was just really AO1, remembering stuff. 3 of it was applying the information that you know to the graph. But you will recognise that graph anyway. That graph's not new to you.